So, in the last class we saw how to multiply two polynomials. Given two polynomials with their coefficients, we know how to multiply these two polynomials to get the coefficients for the resulting polynomial. And we have seen a divide and conquer method has given an order n to the power some 1.58 algorithm. But I told you that there is a method which can multiply these two polynomials in n log n time. And in the meantime, we have seen if we have point value representation of these two polynomials given, then the point value representation of the resulting polynomial can be obtained in a very straightforward manner. We just basically multiply the corresponding values to get the point value for the resulting polynomial in linear time. So the idea is to use this multiplication with other things so that we get the multiplication of two polynomials even if it is not given in point value representation. So the idea of first Fourier transform is this. There is a step 1. In step 1 we evaluate. This is the evaluation step. What do we evaluate? Compute extended, I will tell you what do we mean by extended point value pairs representation. So what do we mean by this is this. So suppose we have been given the polynomial px, then we will be computing this pair xi pxi for, suppose this pxi is of degree n minus 1, then this I will take up to 2n minus 1. Remember, the resulting polynomial will have a degree something around 2n minus 2 actually. If there is 2n minus 1 plus 2n plus minus 1 will give you 2n minus 2. But we will for the all purpose we will assume it is something around 2n. So we need 2n minus at least 2n minus 1, including 0, this will be 2n variables. We will be computing all the point value pairs here for p. Similarly, we will also compute the same thing xi for q. So 0 I going from 2n minus 1. So suppose we compute this once, so in the next step, step 2, we will multiply. So this is pointwise multiply. This is the next step, pointwise multiply. In this step, we will compute yi, which is nothing but p of xi and q of xi for 0 I to n minus 1. And in step 3, so this will give us the value for the point values for the resulting polynomial of px qx. So now we have this point value representation. To get the actual polynomial form, we have to convert this form to the actual polynomial form. So that is step 3. So that will be the interpolation step. So that is interpolate. So in this interpolation, we have to compute R0, R1 up to R2n minus 1 such that yi is equal to r of xi for 0 I to n minus 1. So once we compute these 2n values, the 2n coefficients, then we have got the resulting polynomial. Okay, so these are the major 3 steps: evaluate, pointwise multiply, and then interpolate. We already know that this can be done in how much time does it take? This is order of n. This step is order of n, step 2. So if we can do step 1 and step 3 in order n log n, then we have this entire algorithm in order n log n. So we'll have to basically see how can we evaluate a function at say 2n positions, 2n points in order n log n time. Right now what we know by Horner's rule, we can do it in only order n square time, because each one takes order n, order n values will take order n square. But we will see that we can do it in n log n time. And then also again step 3 we can invert it, or this is the inverse problem of this evaluate problem. So these two are just, one is the inverse of the other in a sense. So this interpolation also, how can we do it in order n log n time? Right now by Lagrange theorem we can use the Lagrange formula to interpolation again in order n square time. So this entire thing right now what we know can be done in order n square time. But if we can do step 1 and step 3 in order n log n time, entire multiplication we can do in n log n time. And this is what precisely done by this Fourier transform technique, that these two steps can be done in n log n time. Now the idea for evaluating a function is based on complex numbers now. So we will evaluate the functions now not in real point. What we will do, we will evaluate the functions only at complex numbers. We only need 2n distinct points, no matter whether it is real or complex, it does not matter. So we will see in Fourier transform we will be using the points as the complex numbers, and they are nothing but the roots of unity. So let us go back to the algebra of complex numbers a little bit. I hope you remember the complex numbers. It has a real part and imaginary part. I will not discuss all those details, but let me just tell you what do you need first. So this is the roots of unity. So the nth root, so we are considering nth root of unity. So one of the roots, say Wn. So suppose we take the one of this root is as W, then we know W to the power n is equal to 1. This is by definition, because then W is an nth root of 1. Now W is an nth root of 1, then there are n such W's. I am denoting each one as subscript W0, W1 up to Wn minus 1. Okay, so Wn I am denoting it as e to the power twice pi I over n. This is called, if you remember, is the principal nth root of 1. Now what is the other roots? So I am denoting it as like this, Wn, there will be a k here. So this is nothing but e to the power I twice pi, then here is k over n, where k is going from 0 to n minus 1. This is just the algebra of complex numbers. This is just by definition. When k is equal to 0, this will give you 1. 1 is a root of 1. Then the next one, when k is equal to 1, that is the principal root. Then k is equal to 2, we will give you another root, Wn2 will denote. then k is equal to 3w3n we will denote. Since there are n such roots, we will have different n values of k, and they are just given by this. And we will be using these roots, this wkn, these n roots of unity as the points where we will be evaluating the function. And we will certainly see if you use this, then we can save a lot of other evaluations. Now, before I go to the evaluation, first let me see how we can represent complex numbers. That is very easy. We can declare something like the type complex. It is a record or a structure in C. It has real part, imaginary part, and you can do something like this. Then you can write function, because we will be needing to multiply two complex numbers. So I am just writing that product so that we don't have any confusion. Suppose A and B both are complex, we want to get the multiplication of A and B. So how can you get that? C dot RE, the real part you will get A dot RE multiplied with B dot real minus A dot im multiplied by B dot imaginary. It is just a formula. Similarly, C dot imaginary will be given by A dot RE multiplied with B dot IM plus A dot IM star B dot RE. So here then you say return C and N. This is a very straightforward. These are just algebraic notations. We already know how to compute the real part of a complex number, which is obtained by multiplication of two complex numbers. How to obtain the imaginary part also. I just use those formula in a straightforward manner here. Now I state some of the properties of these roots of unity. I am going to write some of the properties of the roots of the unity. So one of the property, the first property I am going to write is this w dn dk. I can write this one as wnk. Why does it follow? It follows from this. How would you write w dn dk? By our notation, e to the power I twice pi dk over dn. Then d and d cancels out. This is exactly e to the power I twice pi k over n. So that's why it is w dk by dn is nothing but w kn. It's a very straightforward manipulation here. Then the second one is w n by 2 here. You can see this should be equal to w2 and 1 here, which is nothing but minus 1. It's a very, because this n over 2, this 2 will come below here, 2 will come here, n will cancel out. So you will have the I 2 pi over 2, which I can write as w1 2, but that is exactly minus 1. Then the next one, this is for even n, because otherwise it does not make sense, because n, if n is not divisible by 2, it does not make sense. Okay, the next one is w nk square. If you do the squaring, then this becomes w2kn, and this 2 you can absorb here. So this is nothing but wkn over 2. Again, if you do this manipulation, you will see wkn square is what? E to the power I twice pi k over n, then you are squaring it. So this will be again multiplied by 2, there is 2. This 2 you can write it something like this. You can write it like this, and that's why it is exactly wkn over 2. Okay, that's why this third one, this will be useful for us. Then the fourth one is sigma j going from 0 to n minus 1 W n k to the power j. This is exactly equal to 0 for n greater than equal to 1 and k greater than equal to 1, where k is not divisible by n. If k is not divisible by n, then if you take this sum, then this sum must be equal to 0. So let me just prove the fourth one. I will go quickly over it just to tell you why it is true. So let me take the fourth one. I am just going to give you the proof for fourth one. So proof of 4. You just consider this W n k sigma j is equal to 0 to n minus 1 W k n j. This is the sum which you are interested. I have just multiplied with some factor. Minus I am taking another one, j is equal to 0 to n minus 1 W n k j. This is the one which are interested. Okay, I am just taking this. So let us see what is equal to. Now if you multiply W n k with every term here, it will increase basically the j by 1. So I can write this entire thing as if j is going from 1 to n. W n k j. I can do this because this will go and multiply. Suppose j is say 1, so this is W n k. If you multiply with another W n k, it will give you W n 2k. So j instead of 1 is started as if from 2. So 1 converts to 2. Similarly 3 will convert it to 4. So that sum can be written as like this. From instead of going from 0 to n minus 1, it can go now 1 to n. Now this remains as it is. J is equal to 0 to n minus 1 W n k j. Now if you unravel these two sums, almost every term cancels out except the last term here and here the first term. Everything else are equal and they cancel out. So the last term here will be W n k n and the first term here will be W n k 0. Now W k n n is nothing but 1. You can verify it because this is nothing but W n k n, that will n will cancel out, ultimately it will be e to the power twice pi k, where k is greater than equal to 1, that is nothing but 1. So this will be 1 and this is also 1, so this will be 0. Now if this is 0, I can write, look at this left hand side, this is nothing but sigma, I am writing the left hand side, j going from 0 to n minus 1 W n k j, and here it is W n k minus 1, that is the left hand side, which we have proved to be 0. Now if k is not a multiple of n, then this cannot be 1. If k is not a multiple of n, it cannot be 1, and that is our assumption. So since this is not 0, then this part must be 0. Since W n k minus 1 is not 0 because k is not divisible by n, then it must be true, 4 is true. This part is 0, this goes to 0. So here it is a very straightforward manipulation, algebraic manipulation. There is nothing, no algorithms so far. But these are the properties which we will be using in our algorithm. Okay. So let us keep these 4 properties in mind. So we will go back to these 4 properties one by one. We will see how we are going to use it. Now we start our algorithm, which is called discrete Fourier transform. What is this discrete Fourier transform? So let us assume we are going to evaluate the polynomial px at n different values. of x, and we choose x equal to Wn j for j going from 0, 1 up to n minus 1. So, these are the different n values we are going to choose. So, we have Px is equal to P0 plus P1x up to Pn minus 1 x n minus 1. This is the given polynomial. Define y0, y1, yn minus 1 so that yk is nothing but the polynomial p evaluated at Wnk. We have just taken one of the nth root, the kth one in the nth root, and if you evaluate the polynomial p, that gives you the value yk. Okay. So, by definition now I know that yk is nothing but sigma j is equal to 0 to n minus 1 pj w n kj. Just put the value of x w n k here, you will get exactly this sum. Put the value w n k here as at x, what you get pj w n kj. It's exactly this, x to the power I, put that will give you the j, x to the power j will give you this j here, and you have to take the sum to get the value yk. Now, this vector y equal to y0 up to yn minus 1, this vector is called the discrete Fourier transform, which is called DFT, discrete Fourier transform of the vector p0 p1 pn minus 1. So, you are getting n dimensional vector here from another n dimensional vector here through this transformation, and this transformation is called the discrete Fourier transform, DFT. Now, you can see the major task is to how to compute this discrete Fourier transform very fast. If we can compute DFT from this given vector, then at least the step 1 of our algorithm is done, of our multiplication. Then to get the step 3, we have to compute the DFT inverse. Given a vector, say given this vector, I want to compute this. So, this is just the inverse problem, that is the interpolation. So, that is called the DFT inverse of this. So, we can write y is equal to DFT of p. What does it mean? It means this, or p is equal to DFT inverse of y. So, basically we have to solve the problem of computing DFT and DFT inverse. Computing DFT is nothing but the step 1 of our multiplication, and DFT inverse is the interpolation, the step 3 of our multiplication. So, these two problems if we can solve fast, then we have a fast algorithm for polynomial multiplication. So, let us see how can we do this DFT calculation fast. So, this algorithm, how to compute this DFT fast, is called the fast Fourier transform. That is called the fast Fourier transform algorithm. So, using fast Fourier transform algorithm, we can compute this DFT fast. Now, again, if you remember, the major paradigm of doing this DFT here will be something we already did, the divide and conquer approach. Using a divide and conquer approach, we will compute this DFT. We will split the polynomial into two halves again. So, let us do that. So, I am assuming for the time being n is equal to 2 to the power k. If it is not, you can pad enough zeros. So, I am assuming n is equal to 2 to the power k. Then I am splitting the polynomial p into two halves. One is p0 x, which I am writing as p0 plus p2x. These are the all even coefficients, even in the sense of position, p0, p2. then P4 x square goes up to Pn minus 2 x n minus 2 by 2. It goes up to that. Then I am going to write the other part, P1x. It will take care of the other coefficients which are left, P1 plus P3x plus P5x square. It goes on up to again Pn minus 1 x to the power n minus 2 by 2. So these are the two parts of the given polynomial. No, the given polynomial will be given, can be written as Px is equal to, if you look at these two parts, it is P0x square. It has to be P0x square. Remember, I have written P0x is equal to this, but P2 is actually associated with x square. P4 is x to the power 4. So you replace x by x square, you will get all this. Plus, here you will multiply with x and then put P1 of x square again. Because P1 of x square will give you P3 x square, that multiplied with x will give you x cube. P1 multiplied with x will give you P1x. X square with x square it will give x4, multiplied with x will give you x5, which is right. So Px is exactly this. Px is this. Now let us see how can we compute the DFT of P0 and P1 recursively, and then use those coefficients or the DFT values to compute the DFT values for Px. That's what our goal will be. So for the time being, assume y0 is the vector, DFT vector for P0. So this is DFT of P0. So P0 is a polynomial now up to degree n over 2 minus 1, almost halved. The degree is reduced by half. And you are taking the DFT of that polynomial, that is y0. Similarly, assume y1 is the DFT of the other part, P1. So this, what does it mean? It means this. This means y0 of k, the kth element in this y0 vector is given by P0. You have to evaluate this function at some roots of unity, which will be nothing but wk n over 2 now, not n, because to evaluate a polynomial of degree n minus 1 we used n, but this time this degree is n over 2 minus 1, so you will be needing up to n over 2. You will be needing up to the n over 2th roots of unity. That's why this is. So for this is for k going from 0 to n minus 2 over 2. Similarly, y1k is given by the same thing, P1 wk n over 2, again for k going from 0 to n minus 2 over 2. So these are the two evaluation, y0 and y1. Now let us see how can we evaluate the y vector for the DFT of P. We have not, that is our goal. We need to calculate the DFT of P, but we have calculated only DFT of P0, DFT of P1. So how can we use these coefficients or these elements of the DFT vector to compute a DFT vector of P? If you remember, that will be our conquest step of division, divide and conquer paradigm. We have only just told you how to do the divide step, but conquest step needs to merge the solution of the two parts into a single part. So that I am going to tell you now, and there we will be using this, how Px is constructed out of P0x and P1x. That has to be taken care of. So that we will put those ones here and we will get a new formula. So let me put this. So we can compute y is equal to dft of p. This is what we want to compute as follows. So this you do for 0, k is going from n minus 2 over 2. Yk, how would you get yk? Yk is p of wnk by definition. Yk is, if you put wnk in the polynomial px, that is the yk of this y. When I say yk is the kth element of this vector y. So this is the definition, p of wnk. Now I am going to put now the formula how px is constructed out of p0 and p1, just straightforward substitution. If you substitute, you will see this is nothing but p0, you remember it was x square, so this will be wn k square, and wn k square is nothing but wn 2k, and by formula this is nothing but wk n over 2. So I can write this is wk n over 2 plus x times, that is wnk, x times it was p1 x square. Again we can write p1 wk n over 2. And this is exactly, already we have seen, this is nothing but yk0 by definition. This is the kth element of dft of p0. We just wrote in the previous page, that is the kth element of dft of p0, which is this, plus wnk, this is y1 k. So we have got from 0 up to n minus 2 by 2 all the coefficients yk by using this formula. Let us see, we have to compute another half, that is yk plus n over 2, that those ones will give you the later half, the larger half of the elements of y. So how do we get them? It is again p wn, this is k plus n over 2 now. This I can write as again p0 wn plus n plus 2k. This part, why? Because p0 and you square this one up. If you square this one, it will be w2k plus n, and that is this 2k plus n over n, that is this part, plus x is wn k plus n over 2, then p1, again square it up. If you square, you will get wn n plus 2k, same thing. Now this can be simplified as p0 wn plus 2k n is nothing but w2k n, because wnn, if you separate it out, wnn is 1. So you can write this one as wnn times w2kn, wnn is 1. So that's why w2kn, plus this one remains wn k plus n over 2. Now k plus n over 2, you can write it as minus w, right, exactly, very good, wn k. This will be minus wnk, we can write, and then p1 we can do the same thing, wn 2k. So if you write this, you can express it as yk0 minus wnk y1. 1k. So again, from 0 and 1, these two DFTs you are constructing the two halves of the DFT of P, and this gives you the major tool for your divide and conquer. So in the divide step, you compute the DFT of the two parts recursively, then compute the elements of DFT of P from the y0 and y1 using this formula. And this gives you a straightforward algorithm. Now I am going to give you the algorithm. So what is saving you here? The saving is that you are not computing the polynomial at all two endpoints or all endpoints. You are as if computing half of them and then getting the other half from the already computed values. You are somehow using some of the old values. That's what this one is doing. That's the saving here. And this is happening, if you think a little bit, this is happening because of the symmetry of the unities of the root. Because of the symmetries of the unity of the root, because one root is just in the opposite side. If you represent the unities of a root, it looks like this. If you draw the circle, if you draw the vector, it looks like in the opposite direction. There is this is 1 minus 1, I minus I. So this is I, there is minus I. Then this is something that opposite. So as if you are evaluating the function in one half using some these roots. Other evaluation you are getting from these ones using some of the properties. This symmetricity you are actually using. That's why you are gaining here. Okay. So let me now write down the algorithm. So this is the function FFT. P is the polynomial. Okay. So first we are assuming n is the degree of the polynomial, degree bound of the polynomial. If n is equal to 1, then return P, there is nothing. Else P0 is equal to P0, P2, Pn minus 2, then put P1, the other left part, P1, P3 up to Pn minus 1. So you split it into two parts. Then recursively compute the vector y0 using FFT P0, compute y1 again using FFT with P1. This is the divide step. Now I'm going to write the conquer step. Use w equal to 1 and wn equal to e to the power I twice pi by n. Now here is the combination. Here is the formula which will give you the conquer step. For k is equal to 0 to n minus 2 by 2, do yk is equal to yk 0 plus w y 1k. That is the first part. This gives you bigger. Yes. So I'm going to write. Okay, let me write this one in a bigger one. Yk is equal to yk0 plus w yk1. This is the first formula, if you remember. This is nothing but, let me first write it, then I will explain. Then y n over 2 plus k is yk0 minus w yk1. And here w is equal to w times wn. And for here the last step, I don't have much space, but return y basically once you are done and end. This is the entire algorithm. So let us look at these steps are all clear. This is the divide step. So this is exactly the two formulas we are going to use. So here let us go back to this. You see yk is equal to yk0 wnk y1, that is yk is equal to yk0 plus w times this. Now this w times this is nothing but wnk, because that is getting updated here. You are multiplying w k times, you are multiplying wn k times, that will give you wnk, and that's what it is doing here. W is equal to wnk. Initially w is equal to wn0, which is 1. The next step immediately you will get wn1. Next step it will be wn2, and that's why it is w times this. And then the next formula, this is yk0 minus wnk y1k, which is exactly this yk0 minus w yk1. This w is nothing but wnk in the algorithm, because it is getting updated in every loop. So this gives you the entire algorithm for FFT. Now, how much time does this take? If I express the time of this algorithm Tn is two, we are splitting into two parts and giving two recursive call whose degree is n over 2. So this is 2 Tn over 2 plus order n, that for loop is only order n. You are executing that for loop here n times, and within this each one is a constant time. This is a constant time computation. This is a constant time computation. So total is order n. So if you do this analysis, you already know this solves to n log n. So this is n log n. So you can compute the FFT in n log n fashion. So we have only shown you that how to do the step 1 of that polynomial multiplication in n log n time. Then still the step 3, that is the inverse of DFT, has to be done in n log n time. So that we will cover in the next lecture.